Okay. This week, well, last week we saw several computations using chain rule. This week, we're going to look at some functions we can apply the chain rule to, well, some equations we can apply the chain rule to, and use that to find more derivatives that we couldn't find with just our algebraic derivative rules. So the first one is one like this, where we have x's and y's, but we can't solve explicitly for y. So we have a relation between x and y, but we can't solve this for y. But what we can do is take the derivative with respect to x, and when we do that, dy dx is going to show up in a few different places because of the chain rule. So we have this function, this equation, not necessarily a function, x over y plus e to the 3y equals 4 plus x squared minus cosecant of y. And we're going to treat everything with x's as something with x's. We're going to treat everything with y's as potentially something with x's. And thinking of it like that will help us in going through this process. So we have this equation. We're going to differentiate with respect to x. So the first thing we see is this x over y. So we have two different things. We have x over y. You could, if you want, the simplification would be a little trickier. You could treat that as a quotient. I find it much easier to think of this as a product of x and 1 over y. So we have these two quantities. We want the derivative with respect to x. So we're going to apply the product rule to that piece. Differentiate with respect to x. The derivative of x is 1. I guess I'll write 1 for now. I'm going to erase it in a moment. Derivative of x is 1. Derivative of x is 1. Leave the second alone. So we get 1 over y plus the first, which is x, times the derivative of the second. Now, you could write it as y to the negative 1, and its derivative would be negative y to the negative 2. Starting now, I'm going to use the fractional form negative 1 over x squared, or negative 1 over y squared, because this week and the next 2-3 weeks, we'll see this show up a couple times, and jumping straight to negative 1 over y squared will be convenient for some of the things we do. But the derivative here, with respect to x, would be negative 1 over y squared. But then we need to recall that we are differentiating with respect to x. And when you differentiate y with respect to x, a dy dx will show up by the chain rule. So this first piece, x over y, which we treat as a product, the derivative given by the product rule, derivative of x is 1 times the second plus the first times derivative of the second, which is negative 1 over y squared dy dx. And I'm going to erase that 1 for now because it's in the way. So we took the derivative of that first piece, which required the product rule. Next, we have this e to the 3y. And notice in this first one, again, dy dx showed up only when we took the derivative of something with a y. In the first one, the derivative we took was just the derivative of x. That has no y's. So dy dx is going to show up by the chain rule every time we take the derivative of something with a y in it. So for this next piece, we have e to the 3y. That has a y. Derivative of e to the 3y, 3e to the 3y, and then multiply by dy dx by the chain rule. I'm going to write this a little smaller so the rest of it fits on one line. And And now on the right side, we're still differentiating with respect to x. 4 is a constant, that doesn't change as x changes. Derivative is 0. Derivative of x squared with respect to x is still 2x. Derivative of cosecant of y, well, derivative of cosecant is negative cosecant cotangent. So the negatives are going to cancel. And make it a positive, but we have a y, we're taking the derivative of something with a y by the chain rule, dy dx shows up. Because we multiply by the derivative of what's in there, which is y. So derivative dy dx. Any questions about getting to this line? Okay, so now our goal here is to find dy dx. And notice it shows up 3 times here. Shows up there, shows up there, shows up there. So we have these terms with a dy dx. We can solve this for dy dx by putting them together and putting the other terms together, factoring and dividing. So I'm going to move the things with dy dx to that side, and I'm going to move the things without dy dx to this side. So bring 2x over here, 1 over y stays here, minus 2x. On the other side, we're going to have a few terms with a dy dx. So I'm just going to factor that out now. Cosecant y, cotangent y is there. We're going to bring these other 2 over. Bring this over, that becomes a positive. Bring this over, that becomes a negative. And now everything on that side has a dy dx, so we can factor that dy dx out, which I combine them into one step. And now we need to solve this for dy dx, which should feel the same as solving this equation right here, 5 equals 2x, for x. We have something times dy dx equals something. So we just need to get rid of that something. Over here in this, we would divide by 2. Over here, we're just going to divide by that entire coefficient. So dy dx equals this left side divided by that coefficient. So 1 over y minus 2x all over this. Cosecant y, cotangent y, plus x over y squared. Minus 3 to the 3y. This marker is just about had it. And you don't have to simplify this. That's a perfectly fine answer. Any questions about 1A? So one line of thought you could go through like with this is, now when I first learned this, the way I thought of it was take the derivatives normally and then just throw a dy dx every time you differentiate a y term. And sometimes with a product rule, it is good to slow yourselves down on a product rule and make sure you're writing out the product as it should be, which is why I wrote out all that side work. It helps keep me organized for one of these. Part B, we have y equals x squared plus 3x all to the x squared. So we have here x is in the base and x is in the exponent. Well, there's no general rule that you can apply when you have x's in the base and x's in the exponent and they're different. But what we can do is introduce a logarithm, and that'll turn this right side into a product. It'll turn the left side into some relation. Well, it'll give us, using the left side, a relation between x and y. So if we throw a logarithm on this, we can then apply reasoning similar to part A to get the derivative. So let's do that. Logarithm of the left is log y. Logarithm of the right, we'll use a natural logarithm so we don't have extra constants flying around. Log on the,
Mr. Cameron,
yes.
why did the log turn into a natural log? I kind of forgot.
Well, you could use a regular log if you want, but you'll have extra constants from the derivative. So the natural log is a simpler derivative. So
Wait, so when do I choose when to use a natural log and a regular log?
well, we'll never use a regular logarithm for this. We'll always use I will always use a natural logarithm for this because I don't want extra constants if we don't need them. So I'll always just use the natural log for logarithm applications. So the natural log of the left is just natural log y. Natural log of the right is given by this, but remember we can use the logarithm properties to turn this into a product. So on the right side, we now have a product, and we can take that derivative. Left side, we have logarithm of y. But what we'll do is, just like part A, differentiate with respect to x. On the left, we'll get 1 over y, but then we need to multiply by dy dx by the chain rule. On the right side, we have a product. So we'll need the product rule. Derivative of x squared is 2x. So 2x, leave the second alone, plus the first one. Derivative of the logarithm. Now remember how the derivative of the logarithm works. Derivative of logarithm of something is what? 1 over that thing, and then times its derivative. So 1 over thing times thing prime. And this could be written as a fraction. In the homework, the last homework on problem 1D, many of you did write it as the one fraction. And thinking of it like that is useful for this type of application, where you jump straight from logarithm of something to the derivative of that something divided by that something. And what would we get here? Well, derivative of x squared plus 3x, 2x plus 3, and divide by x squared plus 3x. Any questions about how we got that third line?
Yeah, sorry, do you mind going over how you got the 2x plus 3 all over x squared plus 3x again?
Yes. So right here we have a product rule. So we need derivative of x squared gives us 2x times the second plus the first times the derivative of the second. So right here, this is going to be the derivative of that second quantity, derivative of logarithm of x squared plus 3x. Now, the general form, well, to do this derivative with the substitution, you would let that inside quantity be u. So let u equal what? X squared plus 3x. So dy du is 1 over u. And du dx, derivative here, 2x plus 3. So then the derivative of this second piece would be given by the product of these two. Which is what? 1 over u times 2x plus 3. But then you can write that as just one fraction by combining them. So you get 2x plus 3 over u, which is x squared plus 3x. And in general, the derivative of a logarithm of something will take a form like that, where in the numerator you have the derivative of that something, and in the denominator you just have that something from this same type of substitution. Did that answer your question?
Yeah, thank you.
Yeah, so this square thing is it's a shorthand notation for just log of something. We'll actually see something like that next week also in one of our applications. Any other questions about how we got this line here? Okay, so now we needed dy dx. Well, there's only one dy dx here. This left side, the right side had only x's, so there's not going to be a dy dx. So we can solve this for dy dx, multiply everything by y. That'll cancel out this 1 over y. Left side times y gives us dy dx. Right side times y gives us what? Well, I'm going to leave a large gap there. Just write y times what's on this right side? Well, 2x log x squared and 3x. This second fraction actually does simplify a little because there's an x in this denominator and there's an x there. So I will simplify that. I mean, you don't have to if you don't want to, but you know, I don't want x's all over the place, so I'll simplify. One of these x's cancels down here. You're left with an x plus 3 in the bottom. In the top, you have x times 2x plus 3x, 2x squared plus 3x. So dy dx is y times all of this, and we can just rewrite y in terms of x. Because we do have an explicit relation between y and x. And you don't have to simplify. Any questions about this one? Okay, part C, we have tangent x to the pi. So in part B, our function had x's in the base and x's in the exponent. So to handle that, we threw a logarithm on. This one, what do we have? We have x's in the base, but a number in the exponent. Well, we know how to take the derivative of something with x's in the base and a number in the exponent using our week 5 and 6 and 7 observations. Derivative of something to a number is that number times that something to the number minus 1 times the derivative of that something. And what would the details for this look like? I will illustrate the details, the actual substitution. Well, we have something to a number. Let's let u be that something. U equals tangent of x what is dy du? dy du, well, y is u to the pi. Power rule there gives us that derivative. What's du dx? Derivative of tangent is just secant squared. And then dy dx would then be this times this with tangent x in for u. So this question 1C I actually could have thrown on last week's worksheet. But I put it on this one to illustrate how it's different from a problem like part B, where in part B we had x's in the base and the exponent. If you have x's in the base and numbers in the exponent, or numbers in the base and x's in the exponent, you don't have to go through a logarithm argument. Any questions about this one? This was 1C. Any questions about 1C?
It's so the answer is pi is this pi parentheses tan x to the power of pi to the power of pi subtracted by 1 and then times that by secant to the power of 2x.
Yes.
Oh, cool.
I agree. I think this is a cool type of problem too. It really makes you think more about power rule. We haven't really done much with non-fraction exponents, but the power rule does apply if the exponent is pi. You know, it applies if it's root 2, you know, any number. Cool. Number 2. I will show two different solutions, two different ways you could get to the solution for number 2. We want, for this curve, we want equations for the horizontal tangent line. So we need where the derivative is 0, and we need equations for those lines. So we need to first find dy dx. Well, the way it's written, you know, in calculus, we have rules that tell us we can pull constants out and then work on the variables. So I always like to do that when we have lots of constants. So I'm just going to rewrite this. Pull the constants out front. So that way I could cover the constants with my hand and deal with the variables. So we have here, we need dy dx. Well, we'll differentiate with respect to x. Derivative of x squared with respect to x is 2x. So I'll pull the 2 out front also. Derivative of y squared with respect to x, well, it's 2y, but then you need to apply the chain rule. So you get 2y times derivative of y with respect to x. Zero is or 1 is a constant, derivative is 0. So we need to set dy dx equal to 0. So let's first solve for dy dx and then set it equal to 0. So let's see. Solve for dy dx, what do you get? You get 2/25 y dy dx. Should make that look more like a y. Bring this term to the other side, so negative 2/49x. Solve for dy dx. And what do we get? Well, solve for dy dx. Well, first I'll divide by y. So we get x over y. Then I'll multiply everything by 25 halves. Multiply by 25 halves. That'll cancel out with the 2/25. We already divided by y, so that y isn't there. That'll solve for dy dx. Multiply the left by 25 halves, multiply the right by 25 halves. 25 and 49 aren't going to go away. But the 2 and the 2 do go away. All you're left with is the negative and the 25 and the 49. Any questions about finding dy dx? This is one of those problems where if you aren't careful with the constants, it can get disorganized pretty quickly. But I always like to, I always do like separating the constants so I don't even have to think about them. Any questions about finding dy dx? So we need equations for horizontal tangent lines. We need to find where dy dx is 0. So let's set it equal to 0. What do we get? We get negative 25 49ths x over y equals 0. Divide by the constant, you get x over y equals 0. Solve this, you can multiply both sides by y. And you get x equals 0.
Mr. Cameron.
Yes.
Okay, so when x over y times negative 25 and 49, how come, why did it disappear? Like
So to solve this, the first thing I did was divide by the constant. So divide both sides by negative 25 49ths. That'll cancel it on the left. 0 divided by that constant is still 0.
Oh.
So we have our point at which, our points at which the derivative is 0 must satisfy x equals 0. Well, the point is given by an ordered pair, so we need corresponding y values.
Professor Cameron,
Yes.
how did you get the x over y to x by itself?
Next thing, multiply both sides by y. So the left side times y is x, the right side times y is 0. So we need the y values for our coordinates. Well, if x equals 0, that goes away. You get y squared over 25 equals 1. Solve this for y. Y squared equals 25. X, y would equal positive or negative 5. So we have 2 points to consider. First point is 0, 5. The second point is 0, negative 5. We need equations for lines. We need point and slope. The slope, so I mean, you could substitute up there, you get 0 over some number, which is 0. But remember, we set it up so that the slope would be 0 because we were looking for the horizontal tangent. So the slope will be 0 in each case. But again, you could have gotten that through substitution up there. Evaluated at 0, 5, 0, negative 5. And turning these into equations for lines, y minus 5 is 0 times x minus 0. Y minus 5 is 0. And, with one like that, I do like to solve for y, although you don't have to. This one, y minus negative 5 equals 0. Y equals negative 5. So this was one solution. Any questions about this one solution for problem 2?
How come it's both 5 and -5?
Because we need all values y that satisfy y squared is 25. So we need the positive and the -5. So we're looking for all points because the given curve isn't necessarily a function. In this case, it's not a function because we do get two y values, but we are looking for all points. So we need to take the positive and the negative. Yeah, the directions say all horizontal lines. Tangent. So any questions about this first way of doing this? Now, there is another way you could have done this purely algebraically. Because we know what the given curve looks like. Well, we can figure out what the given curve looks like. Why? Well, let's recall this curve. Set of points x squared plus y squared equals 1 defines the circle of radius 1 centered at the origin. Throwing extra constants on this just stretches out or compresses this circle in the horizontal and vertical directions. Now, why does it hit these 4 points, this circle? Well, if you let x equals 0, you get all y values where y squared is 1. So you get 0, 1, and 0, -1. And similarly, if you let y equals 0, you need all x values where x squared equals 1. That gives you x equals 1 and x equals -1. Well, we just apply the same reasoning up here. Let x equals 0 first. If x equals 0, that term goes away. You're left with all values y, where y squared over 25 equals 1. 5 squared is 25. And -5 squared is 25. So we get what, x equals 0, y equals 5. And down here, x equals 0, y equals -5 from letting x equal 0. And if you let y equal 0, that term goes away. You need x values where x squared equals 49. Well, that would give you 7 and -7. And then these are combined also in a circular fashion, although it's a stretched out in both directions circle. And we call a circle, which is stretched out differently in the horizontal direction than it is in the vertical direction, an ellipse. Now, we wanted horizontal tangents. Well, just like on the circle, it'll have a horizontal tangent there and a horizontal tangent there. Y equals 5, y equals -5. So you could have done this using the graph if you wanted. So you could do it algebraically, you could do it with calculus. Any questions about that second way? Oh, I wrote it as 1 plus x squared. I'll be consistent. Okay, the third one, so in the lecture, we discussed a derivation for the derivative of inverse sine. So here we're going to do the same, but with the inverse tangent. You could do the same thing with the other four. The cosecant and secant have an inconvenient domain restriction, which causes an absolute value to show up. And personally, I don't think it's worth thinking about. But the other four are nice, meaning the derivative of inverse sine, inverse cosine, inverse tangent, and inverse cotangent. They work out nicely. Now, how do they work out? Well, we recall the general formula for the derivative of f inverse. Who knows it? Well, I know it. But I know it only because I've spoken about it about 11 times in the last 2 years. More easily, I find it before, you talk about something a bunch of times, you eventually get it in your head. But before that, I would always have to derive the formula for the derivative of the inverse function. And it's a quick derivation if you're careful with your use of chain rule. So we start with the standard relation for an inverse function, f composed with f inverse goes away and reduces to x. Over here on the right side, we have a composition of functions. We can take the derivative of a composition using chain rule. On the left side, we have just x, derivative is 1. With respect to x, derivative is 1. On the right, we would have chain rule. And here, we have to be careful with our notation. So we have an outside function and an inside function. Chain rule takes the derivative of the first one. So the first one is f, take the derivative, leave the inside alone. But then the chain rule says you have to multiply by the derivative of that inside. And lots of parentheses here. But I personally like sizing my parentheses appropriately, meaning this of x portion is almost insignificant. It's almost in the way, but it is. And I think it should be here for this one. I don't always use the of x, but here I do use it. So here on the right side, we have a chain rule, derivative of the first, leave the inside alone, times derivative of this inside, which is what we wanted, the derivative of f inverse. Well, if we need a general formula for the derivative of f inverse, well, we can get one from here, just like we could solve this equation for x. Solve it for x, you need to get rid of that 2. Solve this equation for that second quantity, you need to get rid of this first quantity. So we'll divide by the first one. So the derivative of the inverse is 1 over this other piece. 1 over that whole thing, f prime evaluated at f inverse. So you could memorize the formula. And I think the derivation of the formula is a nice application of chain rule because it really makes you think about the composition of functions and taking the derivative of the one and then taking the derivative of the other. Any questions about getting here? So in your work, you don't have to show a derivation. You could just use this formula. But we want this formula with f equal to tangent of x. So here we'll let f of x be tangent of x. Well, we need the derivative, f prime, secant squared of x. Maybe I should use parentheses since I use parentheses. So if f of x is tangent, f prime is secant squared, well then f prime inverse is going to be the derivative of tangent. F inverse prime. So, we'll just say F inverse, being consistent with this formula, prime of X is what? Well, it's 1 over F prime evaluated at F inverse. So here we have F prime, and we're evaluating it at F inverse. And we're going to simplify that a little. Any questions about getting here?
Yeah, how did you get tangent of x for f of x when it's inverse?
Because we're going to use a formula. This formula down here gives us the derivative of an inverse function. So we're taking the derivative of the inverse of tangent. So if we let f of x be tangent down here, then this formula will give us the derivative of the inverse tangent. So we're looking for derivative of inverse tangent. This is the general derivative of an inverse function. In particular, we can use it to find the derivative of the inverse of tangent, which is inverse tangent function. I'll write something. I'm just thinking of how to write it in a concise way. Words or notation? Words or notation? Let's use words. So our goal is to find the derivative of the inverse of f of x, which is the tangent inverse. Well, the derivative of the inverse tangent. I hope that didn't make that less clear. Any other questions about getting here? So now we have to simplify this because this doesn't look like what we want it to look like. To do this, I have to erase this down here. But we remember that the inverse trig functions can be interpreted as angles in a right triangle. So here's a right triangle. And to simplify this, we're going to want, I've been misspelling words all day today. This morning in my Math 101 class, within 1 hour, I didn't count to 4 correctly, and then I didn't count to 5 correctly. Okay, want, W-A-N-T. We want, what do we want? Inverse tangent of x. We will want, in order to simplify this angle theta to be the inverse tangent of x. It will simplify conveniently if we arrange the sides so that theta is the inverse tangent of x. Well, what if we rewrite this so that we can figure out the sides? Because remember, regular trig functions tell us about the sides. Well, then, equivalently, we would want tangent of theta to equal x. Well, what's tangent of theta? Tangent of theta, remember, is this going to be on the screen? Yeah, well, tangent of theta, remember, is the opposite side over the adjacent side. Well, if we want this to be x, let's just write that as a fraction, x over 1. We can do that by letting the opposite side be x and the adjacent side be 1. So with this triangle, with that triangle, the inverse tangent of x is theta. Any questions about that? maybe I'll put a so here. We want that, so we use that next line. Okay, so now we still haven't simplified this entirely to what we wanted. We still have thetas all over the place, but we can figure out secant of theta, because here's theta. What's secant? Well, cosine is adjacent over hypotenuse. So secant is hypotenuse over adjacent. Well, what's the hypotenuse? The adjacent is 1. What's the hypotenuse? Well, Pythagorean theorem. X squared plus 1, all under a square root. So what's secant of theta? I should write this a little higher. So cosine is adjacent over hypotenuse. Secant is hypotenuse over adjacent. So in this case, hypotenuse is root x squared plus 1. Adjacent is 1. So secant of theta is root x squared plus 1. And then square it, the square root goes away. I guess I wrote it as x squared plus 1. So secant squared is x squared plus 1, and just substituting there gives us what we wanted. So any questions about this one? So for the argument for cosine is similar to the argument for sine. An extra negative shows up in this step. The argument for the cotangent and the inverse cotangent is similar to this because a negative is going to show up in the derivative as well. So both of those are worth considering. But forming the triangle is very important because it does allow it to simplify. But remember, when forming the triangle, we always are going to want the angle to be exactly our inverse function. Because if we think of it like that, we can then get the sides of the triangle. So the next topic on the worksheet is related rates. Right now, I'm going to skip over number 4, do 5 and 6, and I'm probably going to push 4B off until next week. Now, the topics for next week, well, the worksheet for next week is going to be fewer, the material, maybe I should say the material for next week is more lecture than problems. One of them is like a half-hour lecture to build up to a problem. The material for this week was, several different types of problems you could see. Consequently, next week's worksheet is probably going to be a little shorter, so we will have time to do 4B next week. But for now, I'm going to go to 5. 5. We'll probably be able to get through 4A later. 5. The height of a cylinder is increasing at a rate of 3 feet per second. The radius is decreasing. How fast is the volume changing? So here we have a situation which is changing as time is changing. And we're asked about what happens at an instant during that change. And we can use derivatives to figure that out, because the derivative tells us a lot about an instantaneous rate of change. So this question asks about the volume of a cylinder. So I put this document on Canvas and I printed it out, discussing the volume of a cylinder. So we have here, I need something to point with. Let's use a marker. We have here, where's the camera? There. The volume of a box is XYZ. Why is the volume of a box XYZ? Well, you take this front face, which has area x squared, you extend it z units into the third dimension, and the area would then, or the volume would then be the area of the first, which is xy, times that extension gives you XYZ. Well, the formula for a cylinder is similar. A circular cylinder. Why is the area or the volume pi r squared h? Well, we take this circle, we extend it h units. A circle has area pi r squared. We extended h units. That gives us a volume pi r squared extended by h, so pi r squared times h. On the second page, and this is a discussion of surface area, we'll talk about the surface area next week in one of our applications. But I've always found the volume and surface area formulas for a cylinder hard to remember. But they're much easier, I think, to remember if you just think of it as a circle extending out. Where's the page? So what do we want? We're asked about the volume of the cylinder. Well, what's the question? How fast is the volume changing? So we can rephrase this question using instantaneous rates of change, using derivatives. How fast is the volume changing? So we want to find how the volume is changing as time is changing. So dV dt. When do we want dV dt? Well, let's see what the question says. When the height is 5. When the radius is 4. Does it tell us anything else? Well, yeah, it does. We're going to need to know about the other rates. So as time changes here, volume changes, radius changes, and height changes. So all of our variables are functions of time, which means we can take the derivative with respect to time. But this question says the height is increasing at 3 feet per second. So the height is changing at a rate of 3 feet per second. And then it says the radius is decreasing at a rate of 2 feet per second. So as time goes on, the radius is getting smaller. And just like we had an interpretation of negative velocity, we can interpret this as a negative change in the radius length as time changes. So the rate is a negative. The radius is getting smaller. So any questions about translating this question into a derivative question? Okay, so now we're going to need to differentiate our function with respect to time, substitute and solve. So what do we get? Well, differentiate with respect to time. Remember, V, R, and H are all functions of time. But we can take the derivative similarly to how we took the derivative in 1a. But now, differentiating with respect to time. So derivative of V is 1. But then you apply chain rule. So you get 1 times dV dt. On the other side, well, first we have this constant pi. I'm just going to pull pi out because we have r squared times h. We're going to have to do a product rule there, and it'd be much more convenient if we didn't have to think about pi while we were thinking about the product rule. So we have a product rule. R and h are functions of time. Derivative of r would be 2r, sorry, I did the same thing this morning. I said r instead of r squared. Derivative of r squared is 2r to the first, but then you apply chain rule, and you get 2r dr dt, and then h carries through with the product rule. So derivative of the first is 2r dr dt times the second, which is h, plus the first, times derivative of the second. Derivative of the second, well, we have h. Derivative of h is 1. H is a function of time. So you get dh dt. So just for emphasis, I will underline in each piece what is underlined. Hopefully that shows up as a different color on the screen. Yeah, it looks like it might be. So what is underlined in each piece is the derivative, in this case of r squared, in this case of h. And then the h and the r squared carry along because of the product rule. Any questions about getting to that line? Okay, now from here, we just have to substitute all these numbers and solve. We need to solve for dv dt. Well, it's already solved for dv dt. So just substitute, we get pi times 2 times 20 is 40, times dr dt times -2 gives us a -80. Plus r squared, 16, dh dt 3, 16 and 3 make 48. And then 48 and -80 make a -32. And the pi still carries along, so we get -32 pi. Volume, so we have cubic units, feet cubed per second. So any questions about number 5? So we'll do number 6 and then we'll do 4A. Maybe we'll have time for 4B. I would guess we won't. I probably shouldn't since I didn't do it this morning. So number 6, we begin our discussion of L'Hopital's rule. And L'Hopital's rule is a convenient way to compute certain limits. Limits where you do a substitution argument and you get a 0/0, or you get an infinity over infinity through a substitution thought. So these directions here for number 6 say to use L'Hopital's rule. On a test, it'll never say you have to use L'Hopital's rule. So it'll say, if you do use it, indicate where you use it and why you use it. But here, we will use it in both parts. So in part A, well, we have this limit. L'Hopital's rule applies if it takes a form of 0/0 or an infinity over infinity. Well, what happens when you let x equal 4? You get 16, -24, +8. That's 0 over 16, -28, +12. That's also 0. So here you get a 0/0. Well, when you have a 0/0, you can use this rule called L'Hopital's rule. And what does the rule say? Well, it tells us we can compute this limit by using some derivatives. So that first limit now equals this second limit. The same limit, but a different function inside the limit. We need the derivative of the top function, 2x minus 6, and then we divide by the derivative of the bottom function, 2x minus 7. And now we can take this other limit. And here, we again try a substitution. And in this case, it does work. You get 8 minus 6 over 8 minus 7, 2 over 1, which is 2. So in this case, we were able to use this rule because we had a 0 over 0. Now you can observe in part A that those two do factor, and you could cancel out an x minus 4 if you cancel, or if you factor them. So you don't, I will, well, next week, the first lecture next week, we will see certain equations, certain limits where you necessarily have to apply L'Hopital's rule to figure it out. This week, the limits we can necessarily have to use it. Was that a question or? Okay. So next week we will see some where we do have to use L'Hopital's rule. This week, both of these limits on this worksheet, you didn't necessarily have to apply it. So any questions about 6a? Derivative of the top over derivative on the bottom. No quotient rules. Unless there's a quotient on top or a quotient on the bottom. It's just derivative of the top over derivative of the bottom. Now, this rule also applies if you get an infinity over an infinity. And we can think of that. We have here polynomial divided by polynomial. And as x goes to infinity, a polynomial is going to be dominated by its largest exponent of the term. And now what does all that mean? Well, it means as x goes to infinity, this top will also go to infinity, because as x goes to infinity, x squared goes to infinity. The bottom, as x goes to infinity because x cubed goes to infinity. Now, if there were a negative on them, then you would get a negative infinity. But either way, the rule applies as long as you get an infinity over an infinity. Now, what does the rule say? Well, it says we can compute that limit by taking a new limit. Well, the limit of a new function. Derivative of the top, 2x minus 5. Derivative of the bottom, 3x squared plus 6x. Well, how can we compute this? Well, what happens as x goes to infinity? What do we get? Well, on top, again, we get an infinity. Because that's a polynomial, it's a line. Lines are polynomials. Non-vertical lines are polynomials, I should say. So as x goes to infinity, that top will go to infinity. This 2 isn't going to change in infinity. And on the bottom, as x goes to infinity, x squared goes to infinity, so 3x squared goes to infinity. Either way, we get another infinity over infinity, and we can apply L'Hopital's rule a second time. Derivative of the top.
Mr. Cameron,
Yes.
for L'Hopital's rule, where it says like if it's 0 over 0, you can apply it. Where it says infinity, negative infinity over positive infinity, and the same thing at the bottom. Do they have to be the same type of infinity, or it's just?
They don't. It can be as long as it's an infinity over an infinity. It could be positive over positive, negative over positive, negative over negative. Either way, it will apply. As long as it's an infinity over an infinity.
Wait, so why do we have to apply the L'Hopital's rule a second time, like you're saying right now?
Well, we applied it the first time, and it gave us this limit. And as x goes to infinity, we try to take this limit, as x goes to infinity, the top is going to go to infinity, and the bottom is going to go to infinity. So L'Hopital's rule can apply a second time because we still get a form on which the rule applies. So right here, we're applying L'Hopital's rule to this function. Derivative of the top is 2. Derivative of the bottom is 6x plus 6. And now, as x goes to infinity, the top is going to stay at 2. The bottom is going to go to infinity. 2 getting divided by larger and larger numbers gets smaller and smaller and goes to 0. So you can apply L'Hopital's rule multiple times in one, to one function. You know, if I made this x to the 10th instead of x to the 3rd, you'd have to keep going if you applied L'Hopital's rule. Because, you know, down in this step, you'd have an exponent of 8. Well, actually, you wouldn't have to keep going. If I made this 3 a 10 and this 2 a 9, you'd have to keep going a bunch of times. But you can apply it multiple times as long as you get a form on which it applies. You know, if in the lecture there was one of them, it was probably the second or the third to last one. The form changed from, I think it started at positive infinity over negative infinity, and then it went to negative infinity over positive infinity. And it would still apply in that case because it is a form on which it applies.
Professor.
Yes.
So when I was doing it, I only used L'Hopital's rule once, and you know the section that you squared off.
Yes.
But because of the correct me if I'm wrong here, but because of the exponent rule or something, where if it's bottom heavy, or if the bottom has the highest exponents,
Yes.
it goes to 0. So is it still could I just skip that step, or did I technically didn't show all the work? Like, I'm just wondering. So instead of doing the second,
I know what you're asking. I'm debating what I should. When I phrase a question on a test, I'll be clear. I would have trouble taking off for that if you applied it the first time. So, you know, it says here, use L'Hopital's rule. So you couldn't, you know, if it says to use L'Hopital's rule, which it may, and on a final, I don't know. But without, this limit could be solved without L'Hopital's rule by making that observation degree 3 over, or degree 3 under degree 2, the limit is 0. So if you apply it once, yeah, that's okay. As long as you show why it works if you're asked to use it. So if you're asked to use it and you can use it only once, you may use it only once, even if it could be applied a second time. Yeah, okay. I'll leave the answer at that. But yes, that would be fine by me. Any other questions about number 6? Okay, so let's do 4A. 4B will be next week. 4B is, I would say, significantly more difficult than 4A, and also more difficult than 5, maybe. What does 4A say? What time do we have? Okay, we have 2 minutes. That'll be enough time. 4A, a rocket is launched vertically. Okay. So a rocket is following that line and is tracked by a radar station 3 miles from launch site. So the radar station will be over here. Rocket launches from here, travels up that line. if the distance from the rocket to the radar station, well, the distance from the rocket to the radar station is going to be relevant. So let's draw that. Is changing at whatever, what is the vertical velocity when the rocket is 5 miles from the radar station? So with this picture, we have quantities which are changing, we have quantities which are not changing. This 3 is never changing. But as this rocket goes up, this vertical distance is changing. So let's call it x. This distance from the rocket to the radar station, as the rocket is going up, is also changing. Let's call it y. So we have quantities which are changing, quantities which are not. Let's translate the question. That says question is asking. If the distance from, what is the vertical velocity? We need the vertical velocity. So we need to find how x is changing as time is changing, because x measures where it is in the vertical direction. So what is dx dt when what? When the rocket is 5 miles from the radar station. 5 miles from the radar station, so when y equals 5. What other information do we have? If the distance from the rocket to the radar station is increasing at 500. So this distance, y, this distance measured by y, is changing at 500 miles per hour. So we also have information on how y is changing. Now I left a gap here above y equals 5, because when y equals 5, we could find the other variable x, because that would make a 3, 4, 5 triangle. So that's what this question is asking. We need an equation. This is a right triangle, so it satisfies Pythagorean theorem. And we get this equation. And now we remember x and y are functions of time, so we can differentiate with respect to time. Derivative of 9 is 0. 9 doesn't change as time changes. X is a function of time, so we get 2x times the derivative of x with respect to time by the chain rule. On the right side, similarly, y is a function of time, so we get 2y times dy dt, because y is a function of time. And now, well, we need dx dt. There's dx dt. So you could substitute then solve. I'm going to solve then substitute. Divide by 2x. 2's cancel. Y over x dy dt. Y is 5. X is 4. Dy dt is 500. And then 500 divided by 4 is 125. And then 125 times 5 is 625. And this is what, miles and hours, I think. So here, our equation we got with Pythagorean theorem, x and y are functions of time. Differentiate with respect to time, rates show up, substitute, and solve. And we won't do B until next week, but B, if you want to practice it again, that angle would be theta. So are there any questions about this one? Yeah, okay, we're 2 minutes over. Sorry about that.